Yes. Now, let's solve the quiz from the previous lecture. Okay, that was quite easy compared to this one, right? So now, let's do it. A particle's position is given by 4 minus 12t plus 3t square, where t is in seconds and x is in meters. What is the particle's velocity at t equals 1 second? How do I find velocity from position? Position is given. I just take a derivative. That's it. Excellent. So v of t is going to be dx dt. What's the derivative of 4? 0. It's just a constant. I don't care about that. How about minus 12t? Just minus 12. 3t square plus 6t. But I'm asked to find v at t equals 1 second, which is going to be minus 12 plus 6 equals minus 12 meters per. Excellent. Minus 6 meters per second. So part A we have solved. Let's move on to part B. Is the particle moving in positive or negative x direction at t equals to 1 second? If I am moving in the positive x direction, my velocity will be positive. If I am moving in the negative x direction, my velocity will be negative. Here, velocity is negative, so particle is moving towards negative infinity. Okay? Now, C. What is the particle's speed at t equals 1 second? What's the difference? What was the difference between speed and velocity?
It does not have direction.
Speed does not have direction. Speed is the absolute value of the velocity. So you cannot say the speed is minus 6 meters per second. Speed is absolute value of v, so it's going to be 6 meters per second. Okay? Excellent. Let's move on. Is the speed increasing or decreasing at t equals 1 second? That's a little bit more tricky than the previous straightforward questions. What is the time rate of change of velocity? Acceleration. Great. So let's first calculate the acceleration. I know that a of t is dv dt. And v I have already found. What's the derivative of minus 12? It's a constant. I don't care about that. 6t derivative is 6 meters per second square. Okay? Now, acceleration is positive. Velocity is, I am sorry, that's not. Velocity is negative. So acceleration and velocity are in opposite directions. What does that mean? Does that mean my speed is going down or going up? Okay, so we're half a split. Let's make this more quantitative. Now, I am moving at t equals 1 second. My v is 6 meters per second. But my acceleration is in the other direction, right? A. So a moment later, just a moment later, just dt later, what will happen to my speed? My speed, v, as you remember, how is it? dv dt is a. So v at t plus dt is v at t plus dt times a. If a is in the opposite direction compared to my velocity, be careful, my velocity will be increasing, but my speed will be decreasing. Okay? Why is velocity increasing? Because my acceleration is in the positive direction. Why is my speed decreasing? Because my velocity and acceleration are pointing in the opposite directions. Okay? So here I can say speed is decreasing. Okay? Plot the acceleration of the particle as a function of time. What's its maximum value? That was a trick question. This is because my acceleration is a constant in time. So the plot is the easiest thing in the world. It's just constant at 6 meters per second square. Okay? What's its maximum value? It has only one value, which is the maximum. So A max is 6 meters per second square. Is there ever an instant where velocity is 0? If so, give the time t. Otherwise, answer no. Okay? Then I'll actually have to go back to my answer. I already found velocity at all times. What does part F ask? Part F wants v of t to be 0. I already have the formula for v of t. I've calculated it. It's minus 6 plus 6t is 0. And from here, I can say that at t equals 2 seconds, v is 0. Okay? Any questions about the solution? This was very straightforward. It's probably below the level of what you're going to see in the exams. Okay? So, let's move to today's question. A drunk driver and someone stopping at a red light. Okay. So, one thing I really emphasize over and over again is in this course, especially in Physics 101, you have to have the habit of reading the question from start to finish before attempting the solution. A lot of our students just jump on the figure, start writing numbers without ever defining anything, and unfortunately arrive at unreadable and wrong results. Okay? So let's slow down. Although I know that in my quizzes, time is a bit of a factor, still, you can relax. You have 15 or I don't know, 10 minutes to solve a question. So you can read it in 1 or 2 minutes. Right? So what does the question ask? You're waiting at a red light in your brand new car. As soon as the light turns green, you notice a drunk driver approaching your car with constant velocity and is 200 meters behind you. You start accelerating immediately. Okay, so let me try to understand the situation. Let's say this is time t equals to t-axis, and here I will plot the position of the drunk driver, xd of t, and position of the sports car. Okay? Now, at time t equals to 0, let's say the light turns green. At that moment, where is the sports car? The sports car is at 0. Let's take this to be the origin. And the drunk driver is at minus 200 meters. So let me call this distance d for now. Now, what defines the motion of the drunk driver's car? We are given that it moves with constant velocity. Okay. So it's just going to be a straight line where slope of this straight line, or maybe let me draw it a little bit faster. Apparently I can't draw straight lines on my computer. Okay. Now, so this is going to be xd. Now, how about the motion of the sports car? It's going to be an accelerated motion, right? So what does the position time graph look like for motion with constant acceleration? It will look like a parabola, right? It's going to tend up. So there are two kinds of possibilities here. If my sports car is accelerating very, very fast, the drunk driver will never catch my sports car. However, if my acceleration is slow, here the drunk driver will actually hit my car from the rear end. Okay. So what do I need to make sure? I need to make sure that my velocity is more than the drunk driver's velocity when he actually just touches my car, right? So I'm looking at a critical acceleration. There are two kinds of acceleration if you want. This is if I'm too slow, and if I'm really fast, I have a lot of acceleration, then I'll actually make it out okay. So there must be a critical acceleration, right, which separates these two kinds of behavior. In that case, what does my curve look like? My parabola will just touch the drunk driver's curve. So it will actually come very close to my car. At that moment, our velocities will be the same. But then my velocity will be larger because I'm accelerating, and I'll just leave the drunk driver behind. Okay? So that's what we need to find out. Good. That's part A. What's the minimum constant acceleration you need so that the drunk driver does not catch your car? How do we, okay, I told you the story here, but we now need to put this into equations, into numbers, into some algebra, right? So let's write the position of the drunk driver as a function of time. I will say, I already called this distance d, so I'll call that it's minus d. And let me call the velocity of the drunk driver v drunk plus v drunk times t, right? So that will be the position of my drunk driver. Is everyone agreeing with me? This is just motion with constant velocity. This is the time to ask questions if you don't understand. No? How about the position of the sports car? Here, it's motion with constant acceleration. What's the initial position?
0.
What's the initial velocity? 0. So I'm just left with 1/2 a t square. Right? So what are the conditions? What am I looking for? At this spatial point, first of all, they must be at the same point, right? So at that spatial point, x drunk must equal x sports. But that's not enough. I need one more condition. I want one more condition. What's that? Their velocities must be equal, so that now I'll actually accelerate and leave the drunk driver behind. Okay? So velocity of the drunk driver at that time must be velocity of, so let's call this maybe TC. Okay? At TC, T collision, So what's the velocity of the drunk driver as a function of time? Well, it's constant, it's Vd. What's the velocity of the sports car as a function of time? Just the derivative of this? No. The integral of that? No. The derivative. I was right the first time. It's just going to be 80. Good. Now, let's equate. I need two equations. The first equation, I will just write minus d plus Vd t collision is equal to 1/2 a times t collision square. Okay? But I don't know what this t collision is. I need one more equation, and it's supplied by the second condition, the velocity condition. So that's going to be Vd is equal to a times t collision. So let's collect, let's solve these two equations. I will call this one, this 2. And let me switch to a better looking color. So in the second equation, I can write T collision is VD divided by A. And I will substitute that to first equation, minus D plus VD. Instead of T collision, I'll write VD over A. And in the other case, I'll write just 1/2 A. T collision square is VD square divided by A square. All right? Let's see what it looks like. So I have VD square over A here, 1/2 VD square over A here, plus D. What am I trying to solve for here? Acceleration, okay? The other two things, the drunk driver's velocity and the distance between the drunk driver and the sports car, is given in the problem. So I'm trying to solve for A. First, let's take this first term on the right to the left. I'll have 1/2 VD square over A is D, or A is 1/2 VD square over D. Okay? Did I reach my goal? What was my goal? Finding the critical acceleration in terms of the given quantities. What was given? D and VD. Let's see. Did we reach our goal? Did we find this critical acceleration in terms of V, D, and D? Yes, we did. So we reached the goal. The second thing was checking the units. What should be the unit of A? A should be meters per second square. On the right hand side, what do I have? VD square, which is meter per second square, divided by D, which is meters. So it's going to give me meters per second square. So the units also make sense. Now, how about some limits? If the drunk driver was not moving at all, what would be the critical acceleration? 0. It will never reach me, right? A goes to 0. That makes sense. And how about the scaling with D? How does it change with D? If the drunk driver is closer to me, I must accelerate faster and faster, right? So as D goes to 0, A goes to infinity, we seem to have all the behavior found correctly. Question? I do not understand the question. Please, louder.
Should we write marginal change?
Okay, so I am writing these down so that you have a way to actually check that your results are correct. What I want all of you to do is to learn these methods and use them in every question you solve. It's going to save you a lot of heartache after the exams, okay? You may have found a different result. And I think it's a good idea, good practice to show these on your paper. You don't have to, but it's better if you do, okay? Now, of course, I was given some numerical values for my velocity D and D. And here there is also one important thing I'll do. I'll not actually calculate all the values, but VD was given as, yes, 60 kilometers per hour. What do you need to do? You need to change this to meters per second, okay? Convert this to meters per second. How do I do that? Well, let's do it. 60 kilometers is 60 10 to the 3 meters per hour, right? How many? 1 hour is 60 minutes times 60 seconds. So I must have 6 10 to the 4 divided by 60 times 60 meters per second. Okay, I'll not actually go ahead and calculate the numerical values. Now, how about part B? What was part B? Part B asked, sadly, although your car looks very good, it can only supply half of the acceleration you found A. Where does the drug driver hit your car? How do I find this? How do I do this? It's again not very hard. In this case, I know that my acceleration is 1/2 the value I found previously. So it's going to be 1/2 times 1/2 d square over d. It's going to be 1/4 vd square over d. What should I do? I'm just asked to find where these two positions are equal. Okay. Use. Okay, so x drunk was minus d plus vd times t. X s is 1/2 all this 1/4 vd square over d t square. From here you need to find what t is, and there you have to find xt of t is. Right. Now, this question required more time than I actually gave in this quiz. Okay. It also was a warning to you that you actually have to take this course seriously. A small and innocent looking question like this can be actually complicated. But I'm not all truly sadistic person, so what I'll do is this quiz is going to be a bonus quiz. Everyone who attended the quiz gets a 10. Okay? That's very good. So it's not going to be graded. Everyone gets a 10. Once in a while, we'll have these bonus quizzes. So it's going to be certainly not every week, but once in a while, we'll have these bonus quizzes. All right? Good. So let's recall what we have. Actually, I see a sense of relief going through the so why are we having these quizzes? We are having these quizzes so you can actually think on physics. And that's unfortunately the best way to make someone think about a problem is to give them a quiz, give them some marks about that. Okay? So now, what have we talked about? We have talked about motion in general up to this point. We said position, velocity, and acceleration are the central concepts we actually think about. To go from position to the moment to velocity, I take a time derivative. Again, from velocity to the acceleration, I actually take a time derivative. And to move in reverse direction, I need to integrate. Right? What else did we talk about? These formulas, the integral and derivative formulas, were general. They applied to all possible kinds of one-dimensional motion. But one kind of one-dimensional motion was very central to our daily lives, because every time we throw something up on the surface of the Earth, it moves with constant acceleration. So motion with constant acceleration is quite important. So we actually can derive the formulas for how position and velocity change when I have a motion which has acceleration which is not changing with time. A simple integration of this is going to give me my velocity as a function of time. It's going to be at plus whatever velocity I have, v0, v at time t equals to 0. And the position at time t will be just again another integral a t square plus v0 t plus whatever position I initially had. All right? So motion on Earth's surface has constant gravitational acceleration. We're going to call this g, and its value is 9.82 meters per second square. Right? Now, in, I guess, 3 or 4 weeks, we'll study acceleration, why this acceleration comes about. The reason for that is gravitational pull of the Earth. All right? We're going to derive this. But today I actually want to tell you a good way to measure it. Okay? How? So let me frame this in terms of a question. And then, so the aim is to measure g. But we want to measure it very, very precisely. How would you measure g? So first way I'll propose is very simple. Throw any object up and measure the time for it to fall back. Okay. Now, so here's the experiment I think of. I'm sending some object with velocity v. It will go up. Whatever goes up must come down. It's going to come back. And what I'll actually measure is time it takes for it to fall back. Okay? Let's calculate this time. It's not going to be hard. Let's say that this is my y-axis. What's my acceleration in the y direction, y-axis? Is it going to be g or minus g? Minus g, right? The objects are falling in the negative y direction. They are accelerating in the negative y direction. So my acceleration is minus g. So if I start my motion with velocity v0, my velocity at later times will be minus g times t plus v0. And my position as a function of t will be minus 1/2 g t square plus v0 t plus whatever my position at time t equals to 0 was. Now, the way I put my axis is I'm going to say that y0 is equal to 0, and I'm throwing this up with velocity v0. So this is 0. So can you tell me how can I find the time of flight? How long does it take for this object to go up and come down? Exactly. Y of t is 0 in 2 instances. When I first throw the object up, and then when it comes back down. Okay. So y at time t flight must be equals to 0. Must be equal to 0. So let's find it. 1/2 g tf square plus v0 tf is equal to 0. This equation has 2 solutions. Either tf is 0, but that means that at this first instant I'm actually throwing it up from the ground level. And the other solution I can just find by canceling 1 power of tf. I will actually find tf is 2 V0 over G. Not surprising. Quick unit check. TF must be time. What's V0? The unit is meters per second. GA unit is meter per second square. So meters cancel. 1 power of second cancels. 1 over 1 second is second. So at least unit-wise, this is correct. So this is one way to measure G. You throw an object up and measure how long it takes for it to come down. But here is the problem. This formula depends on V0. And it's actually not easy to measure an object's velocity with very high precision. Now, what I would like to, it's easier to measure time differences. All right. So if I, for example, take a laser, shine it onto itself, that's how most alarm systems work, right? If I cross the line, if I throw a stone below that, I can easily actually measure the time it takes for it to cross this level once and cross it down again. Okay, so I can measure delta t can be measured very accurately. Another thing that can be measured very accurately is the distance between two objects. Now, the kind of accuracy I'm talking about is not finding G as 9.82 meters per second. That kind of accuracy you can gain from just throwing an object up in your lab. I'm sure you'll do an experiment to measure G. But I actually want the kind of precision where I can maybe put other numbers here. I want to improve the accuracy of my measurement. And for that, I need to tie this quantity to easily measurable quantities. One thing, as I said, that can be measured very accurately is time differences. Another thing that can be accurately measured is the distance, length between two objects. So here's the next experiment I propose. I'll take one of these laser timers. I'll put another one. And I'll put them on top of each other. What I can do is I can measure the length, the distance between these two laser timers extremely accurately to 1 part in 10 to 8, let's say. All right. And now, here's what I'll do. I'll take some object, let's say a stone. I'll actually throw this up. It's going to cross both lasers, and it will come down. So I'll have two measurements. I'll have what I'll call delta T1, and I'll have delta T2. Two readings. Now, here's my question. Can we calculate G from just delta T1, delta T2, and L? Okay. So that's basically what I would like to find out is find out what is G as a function, some function of delta T1, delta T2, and L. All right? Let's take a 10-minute break. When you come back, we'll actually talk about how to do that.